Welcome back. Still hammering away at spatial statistics. Last time I talked about some descriptive spatial statistics that help you get a handle for where your data are and maybe what data are where. So you can do the wheres and the combination of what's and wheres. I'm going to start going into some more spatial statistics. Many of them are inferential statistics. You can see that there are a whole bunch of tools in the spatial statistics toolbox, and I'm just going to cover the high points and go right over these, so don't get too confused or frustrated if I go over a lot of things really quickly. Remember traditional descriptive statistics, central tendency, dispersion. And then last time I talked about spatial descriptive statistics. There's data location, and there are some dispersions and standard deviations and directional distribution, and you can do weighted versus just spatial. The inferential statistics rely on the null hypothesis. I've talked about this a little bit before, and that in this case is complete spatial randomness. So you can't make any predictions about where things are. When you look at this null hypothesis, you can see that when things are random, the test will give you values that are near the mean, which would be a z-score near 0. The further away you get from the mean, or z-score 0, the more likely you can reject the null hypothesis, so that there's something not random going out on this end, and there's something not random going out on this end. The example I'm going to be using for this video is Idaho block groups. Remember from the census that they have geographies that go down to the smallest level, which are blocks, and they nest as the levels get larger and larger. The aggregation units get larger and larger. And so we're looking at block groups here, which is the second level up of census aggregation. Block groups usually contain somewhere between 600 and 3,000 people, on optimally about 1,500 people. So you can imagine in Idaho, population is kind of clustered, and so in order to have only 1,500 people in a block group, you're going to have a lot of block groups where there are a lot of people, and you're going to have not so many block groups where there aren't very many people. So you're going to imagine that a lot of our cluster statistics for Idaho are going to turn up with the result that yes, there are clusters in Idaho for census. Okay, I already talked about this average nearest neighbor. Remember, that's where you compute how far it is from each point to its nearest neighbor. Compare that to what would be expected in a normal spatially random distribution. And in this case for Idaho, we see the z-score is minus 26. It puts it out here at clustered. So as expected, Idaho is clustered according to this average nearest neighbor statistic. So we can reject the null hypothesis, which is randomness. There's another one we can use called Ripley's K, and that's going to give us clustering at different distances. So we're able to say evaluate the clustering at distance A compared to what random would be, distance B, distance C. And so when you do that, you're able to make a chart of what the clustering is in your data versus what you would expect if it was a random distribution. So if your data is above the random distribution line, it's more clustered than random at these spacings, and if it's below the line, it's more dispersed than random, and in this case that's at these larger spacings. Ripley's K, cluster by location. A lot of information you can give Ripley's K. You can do it unweighted, and what that does is it says, here's what I would expect if it were random, here's what I observed, so here's the difference, and you can graph that. And you can see that if I expected it, this would be random, and up here I have higher number, which means more clustered. So more clustered at all distances in Idaho than random. If I weight it according to the population and not just to the location of the census block groups, I see that it's still clustered, and you can see that the difference here is 66 versus 44 here, so that's even more clustered when you take into account the populations of these block groups. General G statistic is going to tell us whether there are clusters of low values or clusters of high values in our data. Here's the statistic, the measure, and we compare that to randomness, and in this case we run it for Idaho. We see a z-score of 2.12, and that would tell us that the high values are clustered together. If we had low values clustered together, they would be out here. And you can imagine that working in the census, because they don't want to create census block groups where they don't have to. So if anything, the block groups will have on the higher end of the numbers of people than the lower end. So we would expect high values to cluster together where there are a lot of people. What happens when both highs and lows cluster? So if lows clustered, we'd be out here. If highs clustered, we'd be out here. So for this statistic, if the highs and the lows cluster, you're going to get a false reading that it's random. Instead of it being a combination of high and low clusters, it might tell you that it's random, and you'd have to be careful with the statistic. Okay, Moran's I is one of the more popular methods of looking for clustering by location and value. What it does is it takes values of neighbors. So this would be the difference between a value and the average value at two different locations. So if I and j are close to each other, or they're neighbors, then we're going to compute the difference between the value at I and the average and the difference between the value at j and the average. If both of those are positive, so both of them are greater than the average, then we're going to say I is greater than 0. Okay? If both of them are less than the average, notice that a negative times a negative is going to be a positive, so I is going to be greater than 0 still. So either way, if they're both above or both below the average, you're going to get a positive Moran. If one's above and one's below, then we're going to get a negative Moran. So if one of them's above average, one of them's below average, you wouldn't call that a cluster, so you can imagine that I less than 0 is going to be dispersed, and I greater than 0 is going to be clustered. So when we do this calculation, if I is greater than 0, we either got highs and highs or lows and lows. If I is equal to 0, we got balances. If the z-score is greater than 0, more clustered. If the z-score is less than 0, more dispersed. Close to 0, can't tell, could be random. Run it on Idaho. What's our answer? Z-score 16, we're out here, which is telling us clustered. It's not telling us whether it's highs clustered or lows clustered, it's just telling us that it's clustered. Okay, so those previous statistics have been a single number for the entire data set. You can actually make maps that show you how clusters work out, and that would be local clustering. And so there's a local Moran's I to go along with the global Moran's I. When you run that, you're going to have kind of a similar thing here as you did for the global, but you're going to be able to do it locally. So we run it on Idaho. Here's what we get. We get highs and highs down here. We get lows and lows up here. So locally, low values are close to each other in these places, and locally, high values are close to each other in these places. Instead of getting a single number or a single result for the entire state, we can kind of map it out and break it through the state a little more. Okay? Another way we can do this is the GI star statistic, and that's going to tell us about hot and cold spots. High GI star, high value cluster, low GI star, low value cluster. Let's run it for Idaho, and we get another map that's kind of like the local Moran's I, but again it's telling us here that we have high value clusters here and some low value clusters that are kind of around the high value clusters in this area and a couple other dispersed ones, but not so many low value clusters as we got from local Moran's I. We can run local Moran's I at multiple distances to see how the high and low value clusters work in terms of different distances of considering things neighbors of each other. That's quite a quick summary of some of these inferential spatial statistics. Next time I need to kind of wrap this module up, so I'm going to talk about regression, and I'm going to talk about some of the other tools that you can use to get things like directional trends and grouping analysis and things like that. So that'll be the last video in this module. Thanks for watching.